Okay, welcome to part 2 of this video lecture series on Chapter 8, OSPF. I'm going to start talking about OSPF's characteristics. Up until this point, in working with RIP and EIGRP, as we kind of discussed in the chapter on dynamic routing, before we dove into EIGRP, we've been working with distance vector routing protocols. This is a different animal. This is what we call a linked state routing protocol. A distance vector routing protocol manages and measures the usefulness of any given route by how far away it is, the metric, and the vector, the exit interface. A linked state routing protocol creates a much more comprehensive view of the network by understanding all of the available link states, not just the ones which are immediate, but all possible link states. This is what goes into when it calculates the entire the big difference really between a distance vector routing protocol and a linked state protocol is the distance vector protocol really never knows the entire topology of the network, at least, whereas a linked state routing protocol actually does have the lay of the land. This is what makes a linked state routing protocol so quick to reconverge. The initial convergence takes longer and takes more work, but once it has converged the networks, once it knows not only the best route but all possible routes, once it receives a topology change, it can recalculate in a real hurry. So let's talk about the evolution of OSPF, the open shortest path first algorithm. Let's see. So, as I mentioned, OSPF is a linked state routing protocol. It is the linked state routing protocol that we use for IPv6 and IPv4. There's another set of linked state routing protocols, IS2IS and IS2IS for IPv6. And OSPF has been evolving for quite some time. At the same time, RIP was in use. Cisco was developing first IGRP and then EIGRP. So these have been concurrent lines of technological development. Of course, we also have our path vector routing protocols, the EGPs. Really, the only one is BGP, which you will discuss in CCNA4, Connecting Networks, hopefully next semester. Now, so let's see. Okay, so there are some key features of OSPF. And let me see if I can't. This is a bad place for that. Let me move this up here for a minute. Okay, now, good. I really did not want to conceal this administrative distance table down here. As you've no doubt heard me say before in class, this table you need to commit to memory. There's really no two ways about it. You will see questions like this on exams, in the real world, on your certification exams. I can't discuss the specifics of the exam itself. There's an NDA it's wrapped in an NDA, but you really do need to know what this stuff means. Tattoo this on your brain, as it were. Let me actually move this a little farther. Okay, maybe, oh, no, that's better. Okay, so we've got, so OSPF is an efficient, scalable, secure, classless, quickly converging protocol. If there's a topology change, that triggers an update to the topology table, the map of the network, as it were, the SPF tree, the whole 9 yards. OSPF uses Dijkstra's open shortest path first algorithm. Edgar Dijkstra, I believe, was a Dutch mathematician. Don't worry if you accidentally spell it DJIKSTRA. I've done that myself a few times. Now, the administrative distance, of course, as we well know, is the trustworthiness of a given source of routing information. The metric is the usefulness of the route. The administrative distance is the trustworthiness of the source of the information. Now, it is scalable, which is to say it supports a hierarchical design through the use of areas. It is very important when you're doing your OSPF implementation that you get your subnetting right first. If your subnetting scheme is hierarchical, then you can make your network design hierarchical, and it'll be easier to do things like route summarization, and it'll be easier to avoid a little bit, at least, of the overhead that comes with OSPF's speed. The other thing is that OSPF is secure. Now, this is something we will not practice in this course. It is something that you might see, I believe, in CCNA security. V2 supports MD5 and SHA authentication. This is authentication using hashing algorithms. Version 3 for IPv6 uses IPsec for authentication. That is true in part because IPsec was designed as a retrofit to IPv4, but IPsec was designed into IPv6 from the get-go. There was something vaguely resembling IPv5 when they were thinking about the technologies that might have become IPv5. IPsec was one of them. IPv5 never happened. IPv6 did happen, and IPv5, things like QoS and IPsec, which were designed as a retrofit to IPv5, were built into IPv6. That's why I think IPv6, OSPF v6 uses IPsec, because it's already got IPsec. So let's talk about the components of OSPF. So there are three main tables, three main databases, shall we say, for IPv4, for OSPF. The adjacency database, which is to say the neighbor table. And now let me move myself again, because I'm in the way again. Okay, here we go. Good, good. Okay, so then there's the topology table, which is built from the link state database. The link state database, the topology table, that's literally a map of the network. The state of all links on the local network, derived from everything that the router has learned from hearing not only from its neighbors, but it's from its neighbors' neighbors and their neighbors' neighbors, and so on and so forth. These link state announcements propagate through the entire network as the routers share information about the networks that they're in, and also the networks that they are learning from their neighbors. So there's a flood of information at the beginning when OSPF is converging. You also have the forwarding table. The forwarding table is, the forwarding database produces our routing table. These are the routes that are generated when OSPF runs. So basically what happens is, and you can think of each of these things as an input to the next thing. So OSPF starts. It establishes its neighbor adjacencies. It builds a neighbor table. Each router will have its own neighbor table, and you can see this using the IP OSPF neighbor command. And then once it has that information, they start flooding out their LSAs. They build the LSDB, the link state database. And this represents the network topology. When all the routers in the same area have the same link state database, that's convergence. You can see this with the show IP OSPF database command. Then finally, the SPF algorithm, Dijkstra's algorithm, takes the link state database, crunches the numbers, and spits out a routing table. So every router has its own neighbor table and its own routing table, but they all have the same topology table, the same link state database. And you can use show IP route, of course, to look at this. There are 5 packet types. Now, remembering from our the advice I gave you at the beginning of the semester on how to take notes, if you see a numbered list of things, pay close attention because it matters. So we've got our hello packets, our database description packets, link state requests, link state updates, and link state acknowledgements. And we'll talk next about what those do and how they propagate through the network, what they contain. So let's see. So the link state operation, and let me move myself again. Okay, I'm bouncing all around. So, okay, so here we go. So step 1, the routers, and let's do all this from the perspective of router 1. This guy right here on this edge of the network. And so we've got a partial mesh. Every router is talking to at least 2 other routers. These 3 are in a full mesh internally with each other, but router 3 is not talking to everybody else. Now, one of the things, and we'll talk about this again when we get to DR and BDR elections, in a multi-access network where every router has to establish a neighbor relationship with every other router on the subnet, that can get hairy and cumbersome in a hurry. So, link state operations. Step 1. We use hello packets to establish those neighbor adjacencies. Step 2, we use LSAs, link state announcements, to flood the area with the cost and the state of those links. Cost being how fast is it? And this is in terms of the exit interface. So a gigabit interface has a lower cost than, say, a low-speed serial line that's running at, say, a fraction of T1 speed, which has a even higher speed than, say, a DS0 line, like a dial-up line. Anyway, so step 2, every router builds its own topology table. Every router runs the SPF algorithm, generating SPF tree. The SPF tree becomes the routing table. So packets, LSAs, topology, SPF algorithm, SPF tree, routing table. So everyone figures out the shortest path. But again, because this is, and actually let me make this a little bit bigger. Okay, there, that's a little bit better. Sorry, I didn't realize that the bottom of this was cut off. Anyway, so because every router knows about every possible path through the network, say if router 4 drops off the network, and router 1's best path to router 5 was going through router 4, and actually technically it isn't. Let's say router anyway, so let's assume that, okay, from the perspective of yeah, router 3. Let's take router 3 out of the network completely. Router 1 could still reach routers 2 and 5 and 4 because it would know about alternate paths to them. Okay, I'm about to run out of time. The next thing I'm going to talk about is single and multi-area OSPF. We'll spend an entire chapter on that very soon. So thanks, and be right back.